Good evening. Welcome to Fermilab. I'm Tom Carter, your host for this evening. I'd like to tell you about some upcoming shows we have. We have one that's going to be very exciting that's not in the regular schedule. On Sunday, March the 8th at 2:30, we're going to have the Army Jazz Ambassadors. The concert is free. It's going to be great, but you're going to have to get tickets. So if you'd like to come to the Army Jazz Ambassadors, it's going to be here in the auditorium on March the 8th. Just call and get your tickets. So the next show after this evening is Saturday, February 7th. It's going to be Cirque Zuma Zuma, which is going to be an interesting combination of African traditions and modern-day circus. Right? Okay, the next talk is going to be on the understandings of cancer on March the 13th, and that's going to be Dr. Minda Bessel from Lawrence Livermore. So that brings us to this evening's speaker. Everybody pumped up? Okay. Dan Hooper. Okay. So Dan completed his PhD in 2003 at the University of Wisconsin. He was a postdoc at Oxford, and then a David Schramm Fellow here at Fermilab. He's an associate scientist with the Theoretical Astrophysicist group here, an assistant professor at University of Chicago. He's written more papers, can't count them up, on cosmology and dark matter. He's the author of two books available on Amazon. Dark Cosmo, In Search of Our Universe's Missing Mass and Energy, and Nature's Blueprint. Okay, so if you're impressed so far, hang in there, it gets better. Okay, Dan is actually, an accomplished guitarist, right? Okay, when he was a postdoc at Oxford, he actually played in a band with Jem Finer of the Pogues. How cool is that, right? Okay. But here's the coolest part. Okay, Dan is actually in a blues band, the Congregation, who played here at Fermilab on this stage. So in the history of the lab, you are about to hear the only person that has both spoken on dark energy and played blues guitar on this stage. So please welcome Dan Hooper.
That was ridiculous. Wow, quite an introduction. I don't think I can live up to this. So I just want to start by saying how cool it is to have this room filled. We live in a time and place where the common narrative you always hear is that the public's not really interested in science, and that you have to somehow trick or otherwise convince them to pay a little attention to it. But yet here we have 900 or so people selling out the joint. That's great. So especially all the young people in the room, I'm just thrilled to have this sort of interest in the science we're doing here at Fermilab. So I'm going to start by posing a pretty simple question, and then we'll get a little more complicated as it goes on. The question I want you to think about, and everybody think about, is just what is in our universe? Sounds like a very simple question. We all think we have some intuitive ideas about this. We might start by just looking around the room and seeing, okay, there's the stuff in the chair I'm sitting on. There's this wood that makes up this paneling. There's the clothing. There's the stuff that makes up my body, all this stuff. But that's just taxonomy. And what physicists are really interested in is trying to understand what all those things have in common. What are their smallest constituents? Why do they come in the patterns they come in? And how do they work? This is not a new question. This is an ancient effort to try to answer that question. So this is actually a diagram from the 17th century, but it depicts a much older idea than that. This is the classical Greek elements. We can see in the corners, there's the air, earth, fire, and water. This is alchemy as of the 17th century. And this was, at that time, the best answer anyone had come up with to the question I'm posing here tonight. This is the elements as we understand them in the 20th century. This is a periodic table that you learn about in chemistry. And all that stuff I listed a couple of minutes ago, that chair, your clothes, the wood, your body, is all made up of stuff on this table. That's a remarkable accomplishment. All the stuff you have firsthand experience with, we can put on one chart. What's an even cooler accomplishment is the fact that everything on this chart is really just a combination of three things: protons, neutrons, and electrons. If you take those three things and combine them in different ways, you can make all the stuff we have firsthand experience with. And if you asked an astrophysicist or a cosmologist, I don't know, 30 years ago, what was the stuff in the universe, they would have pointed to this and said, probably it's mostly made of this. As far as we know, this is the answer. Mostly hydrogen and helium, in fact, a little smattering of other stuff. But if you ask the same collection of scientists today, they'll show you this plot. And this is staggering. This is crazy, okay? All that stuff in the periodic table makes up about 4% of the matter and energy in the universe today. Okay, so most of that is hydrogen and helium out in intergalactic space, just in the form of free gas. A smaller piece, about 0.4% of everything, is in stars, planets, and other concentrated objects. Okay? The other 96%, we don't know what it is. Okay? We use words like dark energy and dark matter, but the honest fact is we don't have much more than an educated guess about what this stuff is or why it's there, how it works. I'm not going to talk about dark energy today except for a few seconds now. We don't know what it is, but we know that the universe is growing or expanding at an accelerating rate. Whatever causes that, we call dark energy. We don't know why it's there, we don't know how it works, but it seems to be doing its job. And then the part that we're really, the part I'm going to talk about for the next hour or so is dark matter, which is kind of my area of expertise these days, or the investigation. So I'm going to frame this whole talk around questions. So the next question isn't what's in the universe, but now that I've told you that cosmologists think there's a lot of dark matter in the universe, I'm going to try to explain to you some of the reasons why we've come to that conclusion. Some of the earliest and most compelling evidence we have for dark matter's existence comes from the ways that galaxies rotate or orbit. So here's a picture of a galaxy kind of like the Milky Way. This is what the Milky Way would look like if you got up above it and looked down. And each of these little dots are just a star or a group of stars. And just like planets orbit around the star they are nearby, stars orbit very slowly around their galaxy. It takes about 250 million years, but the sun will go all the way around the Milky Way in that sort of time. A galactic year is much longer than the solar year. So this picture on the left is what a galaxy would look like and what the stars would do if there was no extra matter. So all the matter is the stars, gas, and dust that we see with telescopes. And then here's the same galaxy with a large amount of dark matter in it, about the same amount that we think the Milky Way has. At first glance, they look really similar. These look about the same unless you start paying really close attention. Look out here. See how slowly these stars are meandering. And then look out here. And you can see they're zipping around a lot faster. So the galactic rotation curves, as we call it, look really different when you put dark matter in a galaxy. And we see this in hundreds and hundreds of galaxies we study in detail. We also see evidence of dark matter in bigger systems that we call galaxy clusters. A galaxy cluster is just a bunch of galaxies gravitationally bound to each other. The Milky Way is in part of a cluster we call the local group. It's not a very creative name, but that's the one we're stuck with. So this is actually a very special system. It's not just a galaxy cluster or a cluster of galaxies, but it's a pair of them. One here and one here. And about 100 million years ago, they underwent a collision and passed through each other. That gives us a very special opportunity to study the dynamics of these systems. I'm going to tear this image apart and show you one piece at a time now. So first, this is what the direction of the sky in question looks like in optical wavelengths. So this is what it would look like if you just could look at it with your eyes, so in visible light. These bright things, they kind of look like stars, but they're actually individual galaxies. So these are all galaxies. Then this red or pink stuff, that's where an X-ray telescope detects light. So if your eyes could see in X-rays, you would be able to see this part of the image. This part, this arc or this bullet-like shape, that comes from the collision. So when these two clusters pass through each other, it created a shock or a wake, and that's the shape of this bullet. And then this part, these big blue blobs, are where we can tell most of the mass is. So basically, this is where the gravity seems to be located. You can see this by looking at how light is deflected around the system as it passes by the cluster. So let's put it all together. The interesting thing is the pink or the red, the hot gas, and the gravity are in different places. So we're looking at an example where the gas collided with each other, slowed down, and the dark matter just kept going. So you could pull apart the atoms from the dark matter, isolating them. And this is the first time anyone saw something like this. And it convinced a lot of people who had been skeptical of dark matter's existence that no, this stuff's real and is abundant in our universe. The third line of arguments I want to present is an explanation that dark matter offers for why galaxies and clusters of galaxies come in the patterns we observe. So the standard picture of the Big Bang, which is empirically confirmed in lots and lots of different ways that I won't be able to go into today, says that when the universe was young and hot, everything in it was pretty uniformly distributed. There was about the same amount of stuff everywhere. This is a dark matter simulation I'm about to run. This is what the universe looked like in the early universe. All these dots are a chunk of matter, in particular dark matter. And we're going to let that dark matter evolve through the force of gravity. And here we go. You can see slowly the dark matter collapses under gravity, forming dense clumps of stuff we call halos. And that's what it looks like now. These sorts of dots are all individual galaxies or halos around galaxies. And then the big clumps of clumps, those are clusters of galaxies or superclusters. The really remarkable thing is if I showed you this map, and then I showed you a picture of a map of galaxies that were actually observed in cosmology, in space, you wouldn't be able to tell them apart. These simulations predict what the large-scale structure of our universe should look like. And we don't have an explanation for that unless there's dark matter. And then the fourth and final argument I'm going to give as to why cosmologists have become convinced that dark matter exists comes from this map. Give me a show of hands if you've seen this map before. OK. Yes, a lot of you, but not all of you. That's kind of what I expected. So this is something we call the cosmic microwave background. So 300,000 or 400,000 years after the Big Bang, the universe was several thousand degrees in temperature. And I don't mean some places where, I mean the whole thing. All of space permeating the entire universe was full of 5,000 degree plasma. It turns out that that's about the temperature where you can melt atoms. This is a phrase that's not used much. I don't know why, but I think that's exactly what's going on. If you heat up an atom to about 5,000 degrees, the electrons and the protons don't stick together anymore, and they become free. Okay? So before that point, when the universe was hot, you had electrons and you had protons, but you didn't have any bound atoms. And then you reached a point where it cooled enough, and they became complete atoms, or they became solid atoms, if you will. And suddenly the universe changed, and it released a whole lot of light, and that light has been traveling through space, cooling ever since. And we can detect it with radio telescopes and microwave telescopes. And this is that map. I think they're red. I'm colorblind. The red or orange points are the hottest parts of the cosmic microwave background, and the blue are the coldest parts. They're just slightly hotter and colder than other parts of the sky. So cosmologists can take this map and use it to learn not only what the universe was like a few 100,000 years after the Big Bang, but how it's evolved and changed ever since. This is the sort of plot we make with that data, and don't let it intimidate you. It's actually really simple. This bump here just means that most of the little fluctuations on here are about 1 degree in size. So something about twice the size of the moon. Okay, that's like a typical hot spot or cold spot is about that size. There's some stuff at smaller angular scales and larger angular scales, but most of it's here. The line through these points, these measurements, are our best fit cosmological model. And that includes some dark matter and dark energy and all this stuff. If we changed the amount of dark energy in the universe, or the amount of atoms in the universe, or the amount of total matter in the universe, or whatever, you change that line. So we can turn all of these knobs in our model until we get the best possible fit. And when we do that, we can reach this conclusion. About 85% of all the matter in the universe isn't atoms. It's this other stuff we call dark matter. Cool, huh? All right, going back to the theme of questions, I hope I've convinced you that, well, you shouldn't really be convinced that dark matter exists, but you can take my word at it that cosmologists are pretty convinced at this point. If anyone can convince you of something that complicated in 5 minutes, you're too gullible. But we're convinced, and you should take our word. So the thing we'd really like to know, and the thing that I would really like to know and have spent the last 15 years or so thinking about, is what is this stuff that we call dark matter? A kind of a companion question is, if all this dark matter is out there and we can't see it, why can't we see it? Why is it so dark? Or if you turn the question on its head, why is ordinary matter so bright? Or why can we perceive ordinary matter? When I look at that podium, why is it giving off light that my eyes can detect? And for that matter, when I put my hand into this wall, why does it stop? Why do I feel this? Why doesn't my hand just go straight through that wall? After all, my hand is basically empty space. The fraction of the volume of my hand that atoms are actively occupying is minuscule. And that same thing is true about the wall. So when I put my hand into the wall, you might have expected that my hand should have passed straight through it, but it doesn't. Does anyone know why? Unless you're in the first 10 rows, I can't see your hand. So here, what's that? Electromagnetism. So it turns out that there's a lot of stuff with electric charge in my hand, the protons and electrons, and in that wall. And when I push my hand towards that wall, those electrically charged particles push against each other. And that prevents my hand from going into the wall. So it turns out that the reason light is emitted, reflected, or absorbed by stuff is because stuff in it has electric charge. Something without electric charge will be dark. And ordinary matter is bright because it has electric charge. To kind of generalize this argument, think about the 4 forces that physicists have identified in nature. By far the weakest of these forces is gravity. It's basically not measurable in the laboratory. We can barely tell there's gravity between atoms. It's extremely feeble. And then there's the electromagnetic force that we were talking about. There's also the strong force and weak force. These you only notice in subatomic physics for the most part. The strong force, though, as its name implies, is very strong. If dark matter interacted through the strong force with atoms, we would have detected it a long time ago. So what we learned from this is whatever dark matter is made of, whatever kind of substance it is, it better not feel either of these 2 forces. It can't have electric charge, and it can't have the stuff we call color. It's not the kind of color that you know about, but it's the same word. It's confusing. It's this thing that makes you feel the strong force. Whatever the dark matter is made of can't feel these 2 forces. This chart shows every kind of matter we understand in the universe. Okay, so all the stuff on the periodic table is made up of these guys, basically, along with the electron. These 6 quarks are all the things that are strongly interacting in nature. These 6 leptons include the well-known electron, the neutrinos that you've probably heard of, and a couple of other particles. And then these are the particles that carry forces. The photon is why there's electromagnetism. The gluon is why there's a strong force. The W and Z is why there's a weak force. And then there's the Higgs boson that's been all over the news since it's been discovered a couple of years ago at the Large Hadron Collider. Let's contemplate for a second whether any of these known types of matter or energy might make up the dark matter. Well, the first thing we can do is rule out anything that feels the electromagnetic force. So I've crossed out everything on the chart that has electric charge. That's a lot of it right off the bat. That simplifies the problem. Now let's carry it one step further and rule out everything that feels the strong force. And again, the quarks get doubly ruled out. The gluon's gone now. And we're left with a few options, the Z, the Higgs, and the neutrinos. But now we also have to require that the dark matter is stable. And that rules out these guys, the Z and the Higgs. And what I mean by that is if all the dark matter were made up of Higgs bosons today, tomorrow there wouldn't be any dark matter. The stuff decays in a fraction of a second. It doesn't play the kind of role we're hoping to play. And we're left with only the 3 particles that are called neutrinos. And they look like the kind of thing you'd want to make up the dark matter, except it turns out that they're really fast moving, or we like to call it hot. And that just doesn't look like the stuff we call dark matter out in the universe. So none of this stuff seems to do a good job of explaining the phenomena that we observe in dark matter. This might sound like a catastrophe. But where some people might have seen a catastrophe, particle theorists see a playground. I spend like several hours a day just brainstorming new crazy ideas of what dark matter might be. It's great, all right? This is a plot that a friend of mine, Tim Tate at UC Irvine, made. It's his artistic impression of some of our ideas about what dark matter might be made up of. Some of these ideas are really well-motivated, elegant particle physics frameworks, like supersymmetry you might have heard of. Some of them involve extra dimensions of space. Some of them involve neutrino-like particles with even weaker than weak interactions, and many, many other things. The point is we have all sorts of ideas for what the dark matter might be. And there's even a good chance that whatever it really is isn't on this chart or anyone's mind yet. We just don't know what it is, but we have lots of ideas. And what we really want to do is to find a way to test different ideas and eventually figure out what the characteristics of dark matter are and maybe where in this or whatever plot it might fall. We have 3 different classes of ways that we do experiments trying to test these different theories, trying to figure out what kind of matter the dark matter consists of, what kind of particles. There's using big machines like the Large Hadron Collider. They're big underground detectors. We call them direct detection experiments. And then telescopes. Let me go through each of these briefly. This is, it's not the Tevatron. It kind of looks like Fermilab, but this is the Large Hadron Collider in Geneva, Switzerland. It's been in the news a lot. It's currently shut down, but it had been running for the last few years, and it will be running again at a higher energy later this year. It's a 17-mile underground tunnel. Around that tunnel, particle beams are accelerated by powerful magnets to, I think it's 99.9999997% of the speed of light, so virtually the speed of light. And then those beams are collided head-on inside of these giant machines, we call them particle detectors, hundreds of millions of times a second. When you collide these protons together at such high speeds, you put so much energy in one place at one time that you can manufacture entirely new kinds of matter. So this all just comes down to the simple formula E equals mc squared. E for energy, m for mass. If you want to create something with a lot of mass, you put a lot of energy in one place at one time. You can create new things with a lot of mass. So this is how you discovered the Higgs boson a couple of years ago. This is how we discovered the top quark back at Fermilab back in the 90s, and all of those other particles we see on these charts. It's possible in the next run or other future experiments at the Large Hadron Collider that we could be manufacturing dark matter in a way that we could observe and detect. The second class of experiments are what we call direct detection. And it takes advantage of a pretty simple observation. So do an experiment with me. Hold up your hand. Put it down. If our leading particle physics theories are right about how heavy dark matter particles are, in that second your hand was in the air, about 10 million dark matter particles passed through it. Okay? So if you can build a machine that can tell when a dark matter particle hits it, you could maybe see these particles simply by just waiting long enough and being sensitive enough. So here's an example of such an experiment. We call it LZ, or Lux Zeppelin is what it stands for. It's in an underground former gold mine in Homestake, in South Dakota near the Black Hills. It's a Homestake mine. This is for scale. That's a person. And this tank holds a substance called liquid xenon, and it's super carefully instrumented to be ultra sensitive, and if just one per week or one per month or one per year, a dark matter particle recoils off a little bit of that xenon, they can detect it and learn and study the particles that way. And then the third strategy that I'm going to talk about, I'm really going to talk about it for the rest of the talk, is looking not for dark matter particles themselves directly, but instead looking for the kinds of energy or radiation that are produced when they interact with each other. So this is a sort of depiction. So we have two particles coming in. Maybe these are dark matter particles. They interact with each other and become destroyed or annihilate one another. And in part of that reaction, they give off other sorts of particles or energy, and perhaps kinds that we can see, ordinary kinds. And you can try to detect this stuff with any variety of telescopes. Conceptually, this is very similar to a process you may have heard about before. If you take an electron and hold it in isolation, it's stable. Electrons will sit around forever. But if you take an electron and something we call a positron, the antimatter counterpart of an electron, and put them together, they'll annihilate very quickly. And when they do, they produce two photons with a distinctive energy, an energy of 511 kiloelectron volts. Okay? So every time you put an electron and an anti-electron together, they make this distinctive kind of gamma ray. And this is what's behind, for example, the technology we call positron emission tomography, or a PET scan. The idea is you take something like a radioactive nucleus, like fluorine, put it into your body, let it produce occasional positrons. Those positrons annihilate with nearby electrons and give off this distinctive gamma ray radiation. And you detect those gamma rays and make a map of your brain like this. Okay. So we're essentially going to try to do the same thing with dark matter. So instead of looking for 511 keV gamma rays, we're going to look for a different kind of gamma ray that comes from the annihilations of dark matter particles. And this is the tool, this is the PET scan for dark matter that I'm going to use. Okay? It's called the Fermi Gamma Ray Space Telescope. It's a satellite in orbit presently. It's been in orbit now for 6 years or so. And it is, in my view, the greatest gamma ray telescope ever constructed by anyone. It's an amazing instrument. Here's its view of the sky. So this is the plane of the Milky Way. So that's where the middle of our galaxy is. This is straight north and straight south of that center. And you can see the whole plane of the Milky Way is kind of lit up in gamma rays. Oops. Here we go. Kind of lit up in gamma rays. If you could turn it 90 degrees, you would see the spiral arms and everything. But since we're looking straight into it, you just can't tell that. You see a number of features here, like this guy. This is a big, bright pulsar that happens to be nearby. This thing is something called a blazar, which is really a supermassive black hole, a very, very long way away from our galaxy that happens to be shooting its particles in our direction. And you can see any number of point sources and other astrophysical objects in this map. If many of our particle physics theories are right, not all of them, but if a large fraction of them are, you should expect under this map, if you could really dig deeply into it, a pattern that looks a lot like this. This one in the lower right. This is what dark matter annihilation should produce. It's bright in the galactic center because that's where the most dark matter is. And it should produce a roughly round or spherically symmetric pattern of gamma rays that gets much brighter as you move in towards the center. This is the signal that we're going to be looking for in this data set. All right, so let me give you a timeline of how this story has played out so far. And I'm not going to give you the impression that this story has resolved. It is a long way from resolved. It is still very much up in the air, but it's developed a long way since the story started back in 2008. 2008 is when the telescope was first put into orbit. This is it's the vehicle that brought it into orbit. It's called a Delta rocket. This is one of NASA's main large payload tools. And just over a year later, the data that it had been collecting to that point became publicly available. So let me explain what that means. That means that if any one of you had the wherewithal and ambition to study this gamma ray data, you can go to the Fermi website and download it and start working with it yourself. It's probably going to take a while to figure it out. It took me a long time to figure out how to use it. But it's there, and it's publicly part of the public domain. Sometimes I'm going to be talking about the Fermi collaboration, and by that I mean the people who run the experiment, who built it, and who are kind of the caretaker of the data. But just because they ran the experiment doesn't mean the rest of the scientific community can't use the data, or for that matter, the community at large. So just to be clear. So the data became public in August of 2009. And then a couple of months later, just in August of the same month, Lisa Goodenough, who was a grad student at the time, and I wrote our first paper on this data. So Lisa was really important in this analysis because I'm not good at computing, okay? I write code in a language that was written in the 1970s. I plot in this antiquated thing called top drawer, and people make fun of me. Yeah, I'm very, very old school in my computing, and Lisa helped bridge that gap, but we worked together very well in that sense. She was a student at New York University at the time, but she was spending a lot of time at Fermilab, and we had a number of good collaborations around that time. Here's the paper that we put out that October, Possible Evidence for Dark Matter Annihilation in the Inner Milky Way from the Fermi Gamma Ray Space Telescope. We saw that just to kind of reiterate, we studied these gamma rays, and we found that the distribution on the sky and the energy spectrum were both well described by a dark matter annihilating model. Okay, so it looked kind of like the thing we were looking for, and we thought that was pretty cool. Here's an example of one of the plots that appeared in that paper. These are all the gamma rays from the inner 3 degrees around the galactic center, and we saw this bump. And this was the sort of bump that these dark matter theories had long predicted. And we thought, maybe that bump comes from dark matter. We weren't sure. In fact, we said we can't exclude the possibility these photons originate from some sort of astrophysical source or sources that happen to look like dark matter. And I think that was about the correct evaluation at the time. Nothing stronger than that could be said at the time. And we were pretty enthusiastic and perhaps naive. We thought the people in the Fermi collaboration would like this paper, and maybe it would spur further investigation into this topic. That was not the reaction we got. Here are some quotes that appeared in the press shortly thereafter. This was the most polite one. Julie said, "The Galactic Center is a very challenging region." That was her way of saying, these guys almost surely got it wrong, but it's hard, so you can forgive them for it. Jan Conrad, a Swedish guy in Fermi, said, Goodenough and Hooper's proposal is, quote, pretty shaky. And then my very favorite was Troy Porter. This is literally the very first thing Troy Porter ever said to me. The first time I met him, we were at a conference. He looked at my name tag, learned who I was, and didn't say hello, didn't introduce himself, said, "What were you smoking when you wrote that paper?" That was the first thing he ever said to me. So, okay, we were taken aback by our reaction. Okay, but back to the timeline. A few months later, we decided we'd take a look at this data once again. And in fact, in 2010 and 2011, I put out 2 new papers. The first was with Lisa again, and then the second one with Tim Linden, who at the time was a graduate student at University of California, Santa Cruz. And we put out 2 more papers going a little deeper into this data, studying the backgrounds a little bit better, and trying to really scrutinize the signal and trying to separate things that might be dark matter from things that probably weren't. And we thought we strengthened the case considerably. And in hindsight, I think it's clear that we did. It wasn't a bulletproof case yet, but the case did continue to get stronger as time went on. And then starting in 2012, other groups began to look at this data and see the same thing. And that started to get more people's attention. It's one thing when one lone scientist and his collaborators are saying this thing over and over again. But when other groups, including the University of California Irvine group and then the Canterbury group in New Zealand, were finding very, very similar results, I think that started to really get people to pay attention. And then I decided, you know, this is important, and also this is hard. I'm going to need help. So I called some favors in from some of the world's best Gammaray analysts who I thought would work with me to really try to address this in some detail. And here's the collaboration I put together. So this is Tim Linden. He already came up. He was originally a student at Santa Cruz, but he's been a postdoc at the University of Chicago for some time now. So you see, he was quick to join the collaboration. And then I had been working with Tracy Slatcher out at MIT, and she seemed interested in helping, and she brought in her grad student, Nick Rod, shown here. And then we enlisted the help of Doug Finkbeiner, astronomer extraordinaire at Harvard, and his students, Tan Zudalin and Stefan Pertillo. And then the 7 of us spent about a year working on a project that would culminate in this paper. I think in the introduction, it was mentioned that I'd written a lot of papers, and I have. There are a lot of papers, and none of them am I more proud of than this paper. So this was a lot of work. I think we did a really good job, and it wasn't easy. But it was certainly interesting. We found the same excess of gamma rays in the galactic center that all the previous papers had found, but we were able to say a lot more about the details of the signal than we could before. We took a map that looked like this. This is the raw map. And we managed to separate the signal from background in such a way that we were left with just something like this. A couple of things are really interesting about this. For one, this looks about circular or spherically symmetric. It doesn't look elongated along the galactic plane. You don't see a bunch of extra point sources or other confusion. It's a very, very pristine signal, and I think we managed to pull it apart pretty well. And if you just take this part of the signal and look at the shape of its spectrum, so this is the energy of those photons, and this is how bright they are, you get this bump that looks just like a dark matter model. That line is what a dark matter model would have produced. So we were seeing something that both in terms of the distribution on the sky and in terms of the energy distribution looked like what these dark matter theories had long predicted. It was also really extended on the sky. It was big on the sky. So here's a compilation of different papers. So this is one of my early papers with Lisa. Here's a later paper with Tracy Slatcher and I. Here's the Canterbury group. Here's the Irvine group. And here's our last paper. And all the earlier papers were, looking up here, and you could see the signal, but only in the inner few degrees, or a couple of degrees around the innermost part of the galaxy. Our more recent work showed that this extended way out here to 10 degrees or more. So instead of seeing something the size of the moon, you were seeing something, you know, the size of this. Okay. So here's to make that point. So you can kind of see the galactic plane in the night sky here. And this is the moon. It's red because of the atmospheric conditions. But this is the size of the region that we could see this signal from now. Whereas before you were looking at something like this. We could show that the excess photons extended at least to this far and probably further. And that circle corresponds to this. So the Fermi collaboration got more favorable at this point, which was both refreshing and unnerving at the same time. They put out a press release, or I should say NASA did on their behalf, saying that among other things, that it's consistent with some forms of dark matter and the best evidence to date of this sort of thing. So not all the way to endorsing it, but saying, OK, the signal seems to be there, and it might be dark matter. That's a great step in the direction I was hoping they'd go. And then even more interesting is just a few months ago, for the first time in Japan, a member of the Fermi collaboration said that they were finding the same thing in their own analysis. So they find an enhancement approximately centered around the galactic center with a spectrum that peaks at GeV energies, which is what we find, and persists across all different kinds of background models. So basically, whatever they tried to do with their background model, the signal persisted, and it looked like ours. So those were both very exciting developments in our mind. But just because the signal's there, and just because it looks like what you might expect dark matter to look like, doesn't mean that it is dark matter. The galactic center is a notoriously difficult and complicated part of the sky from an astrophysicist's perspective. So here's an image of that same part of the sky as seen with a series of radio telescopes. And you can see all these different labels of different things. This is a complicated piece of the sky with a bunch of weird, violent, catastrophic events going on at all times. Here's a similar image, but this happens to be at a different set of wavelengths. And you can see here some star clusters, here, here, and here. We see a supernova remnant here. We see something called a radio arc. Most notorious is this thing called Sagittarius A, which is the supermassive black hole that inhabits our galactic center. And you worry that any number of these things might be faking the signal that we're seeing and making us think it's dark matter, when in fact it's some number of astrophysical things we just don't understand very well. Probably the leading hypothesis is that the signal might be made by a population of something like 10,000 millisecond pulsars. So a pulsar is a neutron star. Okay, I'm going too fast. Who knows what a neutron star is? Give me a show of hands. Okay. All right, so only about 20% of you, I'd say. Okay. When a star explodes as a supernova, if it's not big enough to form a black hole, it will collapse down into something that's about the size of Fermilab, but with about the mass of the sun. So wildly dense, crazy dense amount of material, basically made all of neutrons. That's why we call it a neutron star. All the protons and electrons have been destroyed. You basically have a sun's worth of neutrons crammed into something the size of Fermilab. What do you think happens when you take a star that's slowly spinning and squeeze it into something the size of Fermilab? It really starts to spin. So picture a figure skater, right? And they're spinning slowly, and then they pull their arms in and they do this. Okay, well, imagine that, but many, 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 many times more. You take something that was spinning once a month, and it's now spinning at a millisecond scale. So every millisecond it rotates on its axis. As a result of that spinning, powerful jets of particles are accelerated along its axis. So it's spinning really at once per millisecond around this orbit, shooting out these jets. Well, if that were the end of the picture, it'd be a little simpler, but it's not. Those configurations only last for like millions of years, and then they basically fade away. And we know there aren't millions of pulsars, just or there aren't tens of thousands of pulsars in the galactic center that are young and active like that. So we need to invoke a different kind of pulsar to explain that, and those are shown in this picture here. So here's an example of a pulsar. It's long since slowed down and kind of died away, and then it started to suck material off of a companion star. So here's a big giant star next to it, and this pulsar is gradually pulling matter from it, and it's getting spun up in the process. And when it's done doing that accretion, it will be spinning once per millisecond, and it will be in a stable configuration that can last for billions of years. And it's possible that there are tens of thousands of these things crammed in the galactic center, producing something a lot like the signal we're seeing in this telescope. The other possibility that people talk about has to do with the black hole at the galactic center. So this is a computer simulation of the various stars that we observe right around the galactic center, and you can see this is going into the future. But you can tell by the way these things are orbiting that there's something with an awful lot of mass there. It's something in the ballpark of a few million times more massive than the sun. Most galaxies are thought to harbor a supermassive black hole. Ours is no exception. And what we worry about is that if matter were falling into that black hole at times in the recent past, it could have ejected very energetic particles that would have populated the inner galaxy in a way that might have faked the gamma rays we're seeing, or might have produced the gamma rays we're seeing, faking the dark matter-like signal. These are really the two ideas we worry the most about. I think there are good reasons to think that pulsars aren't responsible, and there are good reasons to think the supermassive black hole isn't responsible, but we're not completely certain at this point, and we need more kinds of observations to finally convince ourselves that we're really discovering something new. So we have a puzzle that's half completed, we hope. What's going to fill in these missing pieces could be the Large Hadron Collider. It wouldn't surprise me that much if in 2 or 3 years they start seeing the particles, or start manufacturing the particles of the Large Hadron Collider that we're seeing interacting in the galactic center. It may be that one of these underground detectors, like the one I told you about in South Dakota, maybe that's this puzzle piece, and maybe those particles will show up there. Maybe with the same telescope, the Fermi telescope, we'll see a compatible signal from somewhere else in the sky. Maybe from something we call a dwarf galaxy, or maybe we'll detect a new, smaller halo of dark matter in our local neighborhood. Any of these things might help complete this puzzle and go from a really intriguing signal that very well might be evidence of dark matter to something where we can say we've really made a discovery and nailed it. So in the last few minutes, I want to talk about why this is so interesting. Because a discovery of this kind, if it does turn out to be a discovery, isn't the end, but really just the beginning. In one way, you could imagine this could be the beginning of dark matter cartography. We might be using Gammaray telescopes in the future to map where the dark matter is, including all of its little clumps and clusters and distributions. And it may be that, in any standard atlas you buy in the 22nd century will have a detailed map of all the dark matter and how it's distributed in the galaxy. That's a real possibility if this turns out to be real. We can also ask questions about how the dark matter, these particles we're talking about, how they came into existence in the first place. So in most of the theories I'm talking about, at a point about 1/1000th of a second, or even 1/10th of a billionth of a second after the Big Bang, these dark matter particles were being formed. The universe was so hot, and the conditions were kind of like they are in the Large Hadron Collider, that you'd be producing copious amounts of this stuff. And the fraction of it that survived is the dark matter we have today. But by studying what we have today and how it interacts, we are effectively studying what the Big Bang was like when it created that stuff. We can ask, for a particle that behaves like this, how much of it should have been produced in the Big Bang if the Big Bang was like we think it was 1/1000th of a second after the Big Bang? I said Big Bang a lot of times in that sentence, but I think you understand what I mean anyway. So by studying these particles that exist today, we can look at what the universe was like here, which is something we presently can't do. And then, as a particle physicist and a particle theorist, the questions I'm most interested in are not about any one particular particle, but about how all the particles fit into a broader theory. So I want to know not just is what's the dark matter made of, but how does it fit into the big picture? Is it part of a supersymmetric model, or is it part of a model with extra dimensions? Is it a consequence of some sort of grand unified theory that explains all the matter and force, varieties of matter and force that we detect in the universe? Maybe it has something to do with quantum gravity in some way I can't currently understand, or any number of other things. The point is that every time you discover a new type of matter or energy, it gives you a better idea of how they all fit together. Just like any time you pick up one new puzzle piece, it helps you see the image that might have been elusive otherwise. So I see us right now at an important turning point. It may be that a few years from now, we'll all be convinced that this was really just some sort of mundane astrophysics. Maybe there were 10,000 pulsars that were behaving differently than we expected, and that provides a perfectly good explanation for the data. But if I were a betting man, I think that's probably unlikely. I think it's pretty likely, not a guarantee, but pretty likely that we're really discovering a new fundamental type of subatomic particle in the galactic center, and that this probably makes up a lot of the dark matter in our universe. And that's the most exciting thing that's ever happened in my career, and I hope you find it exciting too. We may be finally sticking our head through the filament in seeing the universe a little bit closer to how it really is. Thanks for your attention. I'd love to take some questions.
The first one here.
For answering the question for the rotational velocities of the galaxies, there are some alternate theories which are trying to answer that question, like modified Newtonian dynamics and all. So what is your take on those theories? Whether it is, I mean, it is too ridiculous to modify the classical mechanics, or these theories are worth considering, or they might provide a challenge for dark matter and other theories?
Excellent question. So astronomers by the late 70s had found that galaxies were rotating in ways that couldn't be explained very easily. And people were starting to talk about dark matter as an explanation. And then in 1983, this guy, Mordechai Milgram in Israel, came up with this theory called MOND, or Modified Newtonian Dynamics. And basically, he said that this thing you learn in your first week of physics, F equals ma, is not exactly right. And if you have very, very small accelerations, it goes more like F equals ma squared. Okay? Perfectly self-consistent theory, or at least phenomenological theory. It works, is all the point. And you could explain why galaxies rotate the way they do without dark matter by changing this simple law of physics. And I think at that point, it was a perfectly viable hypothesis. But since then, we've seen dark matter, or the effects of dark matter in clusters, where MOND doesn't seem to help. We've seen the effects of dark matter in the cosmic microwave background, where MOND doesn't help. And we've seen the effects of dark matter in how large-scale structure forms, and it's not clear whether MOND helps there. So when you take that global piece of data, all the data together, it doesn't seem like MOND is an effective way to do this anymore.
If Hawking radiation is the only thing that can escape from a black hole, why would it be making you think that it's dark matter?
So it's true that once something falls through the Schwarzschild radius or event horizon of a black hole, unless it's radiated out as Hawking radiation, it can't ever get out. But when I talk about the black hole giving off particles, I'm talking about stuff going on more around the black hole. Okay. So here's my black hole, and here's my Schwarzschild radius, and in this whole vicinity around it, where the gravity is super strong but not quite black hole strong, that can do a lot of violent stuff, including producing gamma rays.
So if you don't know what the dark matter is made of, then how do you know at what frequency and at what energy level the radiation created by the annihilation will have?
Yeah, you don't. That's exactly right. So what I can do is I can say, hypothetically, let's say the dark matter particles were 100 times heavier than a proton, just a guess. Okay? And let's say those when they interact with each other and annihilate, they produce jets of quarks. That's stuff we find all the time in particle accelerators. That seems plausible. If that were true, what would the gamma rays look like? And then we test that theory. So we write down any number of hypotheses for what the signal might look like, and then we test them one by one. So we have many guesses, and we do experiments, and we revise our guesses based on those experiments. So we don't, going into it, know exactly what we're looking for.
Hi, Dan. Excellent lecture. Dean from Triton College. Just on the LZ detector, why did we decide to use xenon, and what kind of results from interacting with that atom would we be looking for?
So there are a pretty wide variety of experiments in this direct detection game. Some of them use liquid xenon. Some of them use germanium. Some of them use silicon. Some of them use the one that's being done by some people at Fermilab here uses a C3F8, so carbon and fluorine and such. So there are lots of different options, and they all have different advantages and disadvantages. The xenon in particular has some advantages that it's really heavy, and it's also a noble gas, or a noble liquid in this case. And that enables them to have a really stable configuration, and because of its mass, it's more sensitive to certain kinds of dark matter interactions. So the short answer is it's complicated. There are lots of advantages and disadvantages. And xenon happens to be good for various reasons connected to that.
Hi, thanks for the lecture. That was excellent.
Don't see him yet. Wave your arm.
Sorry.
Good, gotcha.
Given that the universe is expanding at an ever-increasing rate, yet at the same time the density of energy and matter of space seems to be constant, what are the ideas about where all that additional matter and energy are coming from, and wherever they're coming from, why does that not violate the energy conservation law?
Did you say that the density of matter and energy is constant?
Of empty space.
Ah, oh, you mean with dark energy?
Yeah.
Okay. So, yeah, dark energy is awfully weird for this reason, right? If I take a cubic meter of space, it has a certain amount of dark energy in it, and then I let the universe expand, and still a cubic meter of space has the same amount of dark energy in it. That means that expanding piece of space has more energy than it did when it was smaller. So people always throw up their hands and say that violates the conservation of energy. You can't do that. But actually, the law of conservation of energy doesn't really apply to that case. What the law explicitly says is that in an interaction between objects, the amount of energy is conserved, not the total amount of energy in a volume. So you can basically violate that law without running into any problems with our understanding of, say, general relativity or quantum field theory or any of our ground level theories. That's okay to do that, in other words.
Okay, I was thinking maybe there's some evidence of subatomic activity, like if we find out where all this dark energy and dark matter is being distributed, maybe that's a sign that there's some type of atom in a larger universe just making itself known. Would that give us some clue about how string theory works, maybe, once we know where all this dark energy and dark matter is distributed?
So that's more or less what I was trying to convey with this slide. And it's a hard sentiment to convey. But my hope is that by understanding the particle nature or quantum nature of dark matter, it will help guide us towards some sort of bigger theory. So maybe it's a particle that fits cleanly in a theory that we call supersymmetry. And then maybe that would help us understand how grand unification might work, or maybe how quantum gravity might work, or whatever else. There are even theories where the dark matter is a particle traveling through extra dimensions of space. That might have something to do with a string theory, for example, et cetera. I'm only speculating. But the hope is that the more we discover about the kinds of matter and energy that can take shape in our universe, the closer the more tools we have to figuring out the underlying theory, the grand unified theory or the theory of everything that underpins it all.
Yeah, I was wondering, when you're thinking about these kinds of radiation signals coming from near the galactic center, are you presupposing that there's some kind of pair production of particle and antiparticle dark matter? And if so, why are you confident that the same kinds of fundamental conservation laws that give rise to electrons and positrons also give rise to pairs of dark matter particles? Or am I incorrect that that's why you think they might be there?
So you're sort of right, but not completely. So you can write down some theories in which there are dark matter particles and anti-dark matter particles, and they were pair produced and that sort of thing. And that's very close to the analogy with electrons and positrons. And then you can also write down theories where the dark matter and the anti-dark matter are really the same thing. We call them Majorana particles. So there would only be one new kind of particle, and it could be produced in the early universe without an anti-partner version. Either one of those can lead to the sort of annihilation signals we're talking about here. But I do want to say there's another point I want to drive home, which is I wasn't confident when we looked for this that these particle theories were true. They were only one logical possibility, and we were trying to test that possibility. So until the only thing that makes me think something is true as a scientist is data that confirms it. So I'm an empiricist. I don't have strongly held theoretical prejudices, or at least I try to keep them on my sleeve. So I wrote down a lot of theories. Some of them I liked more than others, and then I went out to try to find ways to test them. And I think that's the approach I would advocate in general.
You just
maybe two more questions is.
You just mentioned this briefly, but in terms of an Oscar-nominated film, how does this impact or fit into the theory of everything?
In terms of an Oscar-nominated film, so I mean, I can do some cheesy analogies, but I don't think I'm going to give you a very good answer. I mean, if you're trying to put together a puzzle, the more pieces you have, the more you can get the underlying picture. One more piece might be what kind of particle makes up dark matter. I could give you a different kind of example, and this was supposed to be an illustration. So in theories we call supersymmetry, there are many, many other kinds of particles that exist. And if you were to start to discover some of those, and maybe dark matter might be one of those, you might figure out that there's this new pattern in nature we call supersymmetry, and the space-time behaves in this particular way. And then maybe you'll discover some more aspects of that, and you'll see that it fits nicely into something we call a grand unified theory, and that would get us a lot closer to understanding some of the reasons for why things behave the way they do. And then maybe someday with that information you can build upon it and look for some sort of theory that ties that in with gravity, something we call a theory of everything. But, you know, who knows? I mean, going back to the history of science, you know, when any number of phenomena were observed for the first time, when the electron was discovered, did anyone know that it would lead to quantum field theory? Or when people are doing experiments on the speed of light, did they know that this would lead to relativity? Or when you know, Newton began to contemplate gravity, did anyone realize that it would somehow allow for the unification of the thing that pulls stuff towards the Earth and the thing that holds stars and planets in orbits? So I'm not going to presuppose that I can tell you how this is going to play out, only that that's the way science works. And the more you know, the more likely you are to be able to build a bigger theory that explains more.
I wasn't, this is like really simple compared to all the other questions, but I wasn't quite sure why, I understood like why the star spins when or faster when it's like more condensed, because like, I know like it has to have like some force acting when it's like spins. Like in a motor, electromagnetism causes the axle to spin, so yeah.
Great. So it's the idea is this quantity called angular momentum, okay? And this is something that's conserved. So unless you touch something, you can't give it more or less angular momentum. And if you're big, if you're wide and spinning slowly, you have the same amount of angular momentum as if you're small and spinning quickly, okay? So you've seen the figure skater, right? So they pull in their arms to spin to speed up. So by pulling their arms in, or the star collapsing, in order to keep the same amount of momentum, they have to start going faster. Trying to think of other examples. Go to a merry-go-round. Take all of your friends and put them on the edge of the merry-go-round, and then get it spinning, okay? And then all at the same time, pull yourself to the middle of the merry-go-round. It will suddenly start go faster. Do that experiment, and then you'll understand.
Good job. Excellent.
That's fun.
Dr. Hooper will be up in the atrium to answer any more informal questions. There's a reception, punch in cookies up there. And thank you once again for coming to Fermilab.